Welcome to our next uh, object detection paper. The paper we'll be reviewing today is Uninformed Student Teacher Anomaly Detection with Discriminative Latent Embeddings. That's such a big word here. Uh, we're going to divide this into different parts. So this will be the first part where we just look at the high level of what this paper is all about. In subsequent discussion on this paper, we'll look to some specific aspects of this paper that are very important. So, now the problem statement here is we have a data set. I always like to quickly see what is input, what is output. So if you look at this figure 1, on the top row is our data set, and this data set consists of different items. On the middle row is the ground truth. That's a label of where those data set has some breakages or what you call anomalies. Like you can see here in this nail, you will see that this nail has a cut here. So that's an anomaly, which means that this nail will not be strong enough like other ones. That place can get easily removed. You see, this is the head of a toothbrush. You see that the brush here is missing place here, and you see here that this one is just too longer. I think this is a tab, if I'm correct, but you see that the color here is different from every other one. I really don't know what this one is. Maybe it's a termite. And you can see this one. This is supposed to be continuous, but you see some anomaly here. So this place is supposed to look like this. So that's why the ground truth, they do a pixel-wise annotation, that's segmentation of those points where there are anomalies. And this is their result here. So they showed us their result here. It's based on certain scores, so are able to detect the anomalies. So that is the task in this paper. This figure 1 gives us a high level overview of what the input and what the output is, and what the result of their algorithm is. Okay, you can see the standard deviation of the score, red being the highest. So you see that the red is being the highest. So the more red it is, the more accurate it's able to get it, because the ground truth is actually in red anyway. Alright, so this problem is very important in the industry where you want to do a lot of automation to inspect where there are a lot of manufacturing taking place, and oftentimes you usually have a small percentage of the product coming as anomaly. So one important problem here is that most times in the industry, the products manufactured are going to come clean. They are going to be okay, with no bad sample, with no anomalies. The anomalies will be very few. So that immediately gives us a notion of imbalance in the data set. But in this work, what this company did was they curated a data set which they call MBTech anomaly detection data set. And in that data set, they only curated in the training the samples or items that do not have any anomalies, and they now put in the test set samples that has the anomalies. Alright, so during the training, whatever algorithm or method we're using is not able to spot, is not presented with the anomaly examples. It does not even have the idea of what the anomaly looks like. It's only used to what is right, the correct item. So the challenge is how will the algorithm, how will our model be able to detect anomaly when it has not been presented to one during training? So that's the overview. Now, what they are now proposing is they are proposing a student-teacher framework to address this problem and to do the pixel precise anomaly segmentation. Now, what they train, the student networks are trained to regress the output of a descriptive teacher network that was pre-trained on a large data set of patches from natural images. So now the anomalies are detected when the output of the student network differ from that of the teacher network. So, and they demonstrated improvement over state of the art in a number of data sets, the CIFAR-10 and the MNIST, and also on this data set MBTech. Alright, that's essentially what the work is. So this is an overview of the approach. This is the input image. They have different receptive fields they experimented with. They have the student and the teacher. They have the student network. They have the teacher network. Okay. So this is the prediction. This is the ground truth. Yeah. So we will come back to this in detail, the student-teacher anomaly detection, to understand the details of this. But the high level is that given a training data set with each point I that are anomaly-free images, at least they don't have anomalies, our goal is to create an ensemble of student networks, SI, that can later detect anomalies in the test images, J. So this means that they can assign a score to each pixel, indicating how much it deviates from the training data manifold. Okay, so they have to look at each pixel in the image. No, so for this, the student models are trained against regression target obtained from a descriptive teacher network T pre-trained on a large data set of natural images. So this is the teacher network, which we will come back to and look at in details. Embedding vectors visualized for 10 samples of the MNIST data set. So they also use some other data sets like the MNIST, and they try to run their algorithm on it as well. Okay. Um, this is the objective function they're trying to minimize. The final training loss for the teacher network is given by this. We will come back and look at this in details. So, example of student network for deep anomaly detection. So, this is how they describe how to train the student network to predict the teacher's output on anomaly field training data. Okay. Compute the means and standard deviation. So you have the scoring function for anomaly detection, where they try to score, and we can detect anomaly at various scales by training multiple student teacher assemble pair with varying values of the receptive field. This is what they propose. This is a multi-scale anomaly segmentation. These are some of the results on the MP Tech anomaly detection dataset. This is their result, which are mostly the ones that are in black shows that is the one that has the highest performance with a receptive field of 65. We can see the data set. The data set has different categories. You have the textures category, which has all this carpet grid leather title wood, and you have the object category, which you have screw, toothbrush, you have transistors, yes, all this. Alright, so you can see that in most of the experiment, their method perform better. In the grid, we have this method did better. In the wood, we have this L2 autoencoder did better. In the transistor, we also have the L2 autoencoder did better. But for the other ones, their method did better. So the experiment they carried out, they carry evaluation on a number of data sets. So, and they compare with some other methods, like the one class neural network, one class support vector machine, k-means classifier. They experimented with a number of values for the receptive fields, and in most cases, what they did is they combined the different receptive fields in their own multi-scale approach. So this is an anomaly detection at multiple scales. In this figure, they discovered that when the receptive field is very small, it is good at detecting smaller anomalies like this, but it is bad in detecting bigger anomalies like this, as you can see here. And when the receptive field is very high, like 65, it is bad at detecting the small anomaly. It missed this completely, but it is good at detecting the bigger one. So in their multi-scale, they were able to combine the advantages of the small and the big to make sure they get both the smaller anomaly and the bigger anomaly. They perform experiment on the MNIST and CIFAR 10 dataset too, and they discovered that theirs give a better. We'll come back in detail to look at. So this is the performance for the algorithm on the MBTech AD dataset. This is another one. This is another dataset. You have the MBTech AD dataset. Yeah, the same dataset, but they use different receptive field to see the result. But the one we showed before, let's see, 0.695. Okay, that's what they use to compare with the other methods. So it's the same data set. It's 0.933 super. Yeah. So what they now did is they now use multi-scale, and they use multi-scale to combine all these three together, and these are their results. All right. So essentially, in this work, what they have done is they propose a novel framework for the challenging problem of unsupervised. I don't know why they say it's unsupervised, because actually there's a ground truth label, but maybe when we go into some of the other details, we will know why they call it unsupervised. And they did an assembly training that can be performed hand to hand. One important thing here is that the training set is purely anomaly free. It does not have any anomaly. So the model is trained with no samples of anomalies. And I think the reason why they call it unsupervised is they said assembly training can be performed and purely anomaly without requiring prior data annotation. I guess they did not use the annotation, but we shall see that in subsequent walkthrough. So they can extend their approach to detect anomaly at multiple scales. Multiple scales talking about different sizes, and they demonstrate improvement. Some of their references. Alright guys, thank you very much for listening, and if this has helped you in understanding, please do give us a thumb up, and please consider subscribing for different for subsequent discussion of object detection papers in computer vision. Thank you very much, and see you in the next one.